Exponential functions. Today we're going to look at exponential growth. And this chapter kind of leads off of what we've talked about in the previous two chapters, with chapters 7 and 8. So like I've mentioned before, these chapters are very critical as far as building on each other and remembering what we've talked about in the previous chapters. So some of what we'll do in this chapter you'll recognize, but we'll be either building off of it or kind of looking at it from a different perspective. But in this first lesson, like I said, we're going to focus on exponential growth. Now, an exponential function can be defined with this equation, a times b to the x power. Now, the key here is that a is going to never equal 0, b is always going to be a positive number greater than 0, and also b is never going to be equal to exactly 1. If that's the case, if it meets those criteria, then it's an exponential function. Now this a and b, what they represent is a represents what we call the initial amount. And that's important. The initial amount is or a is always what you start out with. B is what we call our growth factor. Oftentimes that'll be a percent that we write as a decimal. But other times it's just a decimal that they give us or that we have to figure out. Now, whenever that value for b is greater than 1, we're going to be talking about exponential growth. If b is between 0 and 1, because remember it won't be less than 0, it'll always be greater than 0. But if my value for b is between 0 and 1, so we have a decimal there, that's going to be an example of exponential decay, which is what we're going to talk about in the next video. But let's look at a specific situation involving exponential growth, and that's dealing with rabbit reproduction. So in 1859 there were 24 rabbits that were introduced to an area in Australia. However, they reproduced so quickly that 20 years later they were referred to as a gray carpet on the continent. Because a pair of rabbits can produce an average of 7 surviving rabbits a year, we can estimate that the rabbit population multiplied by a factor of 7 divided by 2, or 3.5 each year. And again, the reason why we have that fraction of 7 over 2 is because we have 7 rabbits are going to be produced by every pair of rabbits. So for every 2 rabbits, they on average produce 7 new rabbits. So 7 divided by 2 would give us a scale factor or a factor of 3.5. So if you look at the pattern here that's going on, is we start out with the first year, or before we even begin, I should say, we started out with 24 rabbits. After the first year, if I take 3.5 times 24, I get 84. After the second year, if I take 3.5 times 84, I get 294, and so on, until we get to the point where we get, after 5 years, I've gone from 24 rabbits up to 12,600 rabbits. 5 years more, so 10 years after we started, we've gone from 24 rabbits all the way up to 6.6 million rabbits. So you can see that when you're dealing with exponential growth, things increase rather quickly. Because in this graph here, it illustrates this by the fact they're just showing our first 4 years here after 1859. I should say the first 3 years after 1859. So starting with year 0 of 24 rabbits, the first year after 1859, we were up to 84 rabbits. You can see that the further along you go on your x-axis, or in this case your time or your n-axis, you can see that the steeper the graph is going to get. And that's the way a exponential growth equation is going to look when we go to graph it. Now, an explicit formula for this sequence, by explicit formula they're referring to this definition of an exponential function. Remember, it's going to be your initial amount times your growth factor to the x power. So remember, our initial amount was 24 times your growth factor, which is 3.5, to the x power. Now you can use t, or you can use whatever variable you want. So that's how we set up our explicit formula. And that graph, we call that an exponential curve. And the range of the function is going to be the set of all positive real numbers, because remember, 0 is neither positive nor negative, but The reason why we can say it's the positive real numbers is 0 is not included, because my range, my y's, the lowest amount is actually 24. Even though it looks like it's at 0, this is actually at 24 there. So in other words, the n-axis would be a horizontal asymptote. Because remember, a horizontal asymptote means it's an imaginary line that the graph is not going to touch. And so in this case here, the graph is not going to touch the n-axis or our time. Because the lowest amount of rabbits that we ever had since 1859 was 24 rabbits. Now granted, before 1859 there were 0 rabbits, but that's not what the graph is focusing on. It's focusing on the years after 1859. So we're starting out with 24 rabbits. So here's the key thing, is we're going to figure out how to use that equation, or see how to use that equation. So first off, it's asked us that we're still using the same situation, so it's asked us to estimate the number of rabbits after 2 years and 3 months. Now remember, the time is in years. Well, 2 years and 3 months is not, it's not 2.3. Okay, we need to convert 2 years and 3 months into being just years. Well, 3 months is the same as 3 out of 12, which is the same as 1/4. So 2 years and 3 months, what that means is our time is actually 2 1/4 or 2.25 years. So to plug that into our formula, we take 24 times 3.5 to the 2.25 power, and when you do that, you get 402.13, which obviously we're not going to have 0.13 rabbits rolling around, so it would be about 400 rabbits, you could say, or 402 rabbits would be fine to say that too. Now B we're actually not going to do, and I'll talk about that. It says estimate the time to the nearest 0.01 years, or nearest hundredth of a year, when there were 5,000 rabbits. So here you're trying to figure out the time, because we know that we want to figure out how long it took to get up to 5,000 rabbits. Well, the reason why we're not going to cover this portion of the lesson is because later on in this chapter we're going to look to see how we can do this using logarithms. In this chapter they would do it by graphing. Well, if you don't have a graphing calculator, the only way to do it is by guessing. And so that's why we're going to skip these particular types of problems in this lesson, because I want to make sure you focus on how to do these using logarithms. But we can do letter C. Let's look at that one. This time they want us to use t as a negative number. That does not mean our answer is going to be negative. What this means is that we're going back in time. We're trying to figure out a half a year before, what was the year? 1859. So a half a year before 1859, we want to figure out how many rabbits there were. Because remember, we started out with 24, so we want to figure out at what point, or how many, 6 months previous to that, how many rabbits were there. So to set that up, it's going to be 24 times 3.5 to the negative 1/2 power. So again, negative numbers in this case are not going to mean that we get a negative answer. It just means that we're going back in time. So in this case, when you do it on your calculator, you get approximately 13 rabbits. So that's all you do in 1A. 1B is a completely different type of problem, but the same idea. So here they give us the equation. Excuse me. So why don't you guys take a minute and work this one out on your own. Answer A and C. You don't have to do part B, but answer A and C. And so pause the video and hit play when you're ready to check your answer. Okay, so let's see what you did here for part A. They were nice. They gave you 3.5 hours, so you didn't have to change any fractions to a decimal. They did that for you already. But your equation then would be 300 times 2 to the 3.5 power. When you do that on your calculator, you get 3,394 bacteria. Or you could have even said approximately 3,400 bacteria. That would be fine as well. And to go back in time, we're going to take and figure out, well, after half an hour? Yeah, T represents the number of hours. So going backwards a half an hour, how many bacteria were there? If we started out with 300, it's not going to mean that we take half of that. It's not 150. We have to actually put negative 1/2 into the equation. So it's going to be 300 times 2 to the negative 1/2 power. And then when we do that, we end up getting about 212 bacteria. So about a half hour before we started this experiment, there were 212 bacteria. Now another example of exponential functions would be a function that we've talked about in the past, and that would be the compound interest formula. The general compound interest formula, remember, was this. It was a principal times 1 plus r to the t power. So that's another example of an exponential function. Let's look at some story problems and how you can set up, again, your equation for these. Remember, it's always in the form f of x, or y, equals a times b to the x power, where a is your initial amount and b is your growth factor. So let's look at this one. It says the speed of a supercomputer is measured in teraflops, or trillions of floating point operations per second. In 2005, the Blue Gene/L supercomputer recorded a speed of 280.6 teraflops. Over the last 30 years, the speed of the fastest supercomputers has been growing about 78% per year. Suppose that the growth rate continues and that C of x equal the speed in teraflops of the fastest supercomputer x years after 2005. So again, in this case, x would represent the number of years after 2005. But in order to come up with my equation, I need to first figure out what my initial amount is, my A, and what my growth factor is, the B. A in this case is what we started out with in 2005, is 280.6 teraflops. That's your value for A. B is your growth factor. Now a lot of people would say, well, it's 78%, so it'd be 0.78. Well, that's actually wrong. Percents are kind of tricky. Whenever you're increasing, you always take that percent and add it to 100. If it was decreasing by 78%, we would subtract it from 100. So in this case, we're increasing by 78%. So 100% of what we had before plus another 78%. So it'd be 178%, which as a decimal is 1.78. So that's your growth factor, 1.78. So my equation would be C of x equals 280.6 times that growth factor of 1.78 to the x power. And there's your answer. Why don't you guys go ahead and try the same thing now with example 2b here. So again, we're just looking for a formula. So you want to first identify what A and B are, and then plug it into that formula. So why don't you pause the video and hit play when you're ready to check your answer. Okay, so you should have gotten your initial amount is the 33,871,648. That's the population in the year 2000. B is your growth factor. It's increasing by 1.3% per year. But again, that's increasing, so it's going to be added to 100. So it'll be 1.013 would be your growth factor. So now to write this, to combine these now and write it as a fraction, or write it as a function, it'd be C of x equals that 33,871,648, which was your initial amount, times your growth factor, 1.013 to the x power. So hopefully you have an understanding now of what we're looking for with exponential functions. But the key for today is making sure you understand how to set them up using this formula. A times b to the x power. So the initial amount times the growth factor to the x power. So with that, good luck on your assignment.